Okay, I'm going to kind of do a little bit of a review of the notes I went over in class today on inverse functions, and then I'm going to finish off the examples so that you'll be able to do the posted assignment. So just kind of going back over your notes that you already did, and this will help those that were already learning from home. So we have, for any one-to-one function f of x, g of x is an inverse function of f of x if the composition of functions, so if you do f of g of x and you get back x, if that's true for all x in the domain of g of x, or if you switch it around and you do g of f of x and you also get x for all x in the domain of f of x. So you're basically going to do a composition of functions and you want to get x back as an answer. And if you think about it, it makes sense because you're taking a function, you're doing something to x, and then you're taking another function, and if you get back what you started with, then that's kind of the definition of an inverse, because you're undoing what you did. The notation for that is, and you say this, f inverse of x, don't think of it as an f to the negative 1 power, so don't confuse it with when you have something where you're doing a reciprocal. So then I did some examples. So I chose to do f of g of x. That was just my choice. You could also do g of f of x, which means I was putting g of x inside of f of x. So that's what I did. So I had 3 times, then the quantity x minus 2 over 3. The 3's canceled. I still had the plus 2 there. So the 3's cancel, then the 2's cancel, and I'm left with x. So that means that f of x and g of x are inverse functions. So then in class, we graphed. In y1, 3x plus 2, and in y2, x minus 2 over 3. And then I graphed y equals x in y3 and showed how you can see the symmetry. So notice if I folded this on the line y equals x, the red and blue would match up. So that shows that they have symmetry. I messed with the, if you do zoom square on your window, it will make your graph look more squared off, otherwise, because it's a rectangular viewing window. For example 2, I did f of g of x. So again, I'm putting g of x inside of f of x. You got a fraction, and sometimes you're going to. Remember that the fraction bar means divide, and when you divide by a fraction, it's the same as multiplying by the reciprocal. So that's what I did. The 3's cancel, so I'm left with x minus 4 plus 4. The 4's cancel, I'm left with x. Since I got back what I started with, the x, that tells me f of x and g of x are inverse functions. On example 3, I chose to go the other way, and I put f of x inside of g of x. And when I did, so I took this cube root function, put it inside this, so it became the cube root of x minus 4 quantity cubed plus 4. If you cube a cube root, it cancels out, so you're left with x minus 4 plus 4, which equals x, which shows that g of x and f of x are inverse functions. And I graphed it and showed, and you can kind of see the symmetry across the line y equals x. Then for example 4, we had f of g of x, so I put g of x inside of f of x. Nothing cancels, so I multiplied by 5. And then I found a common denominator, which would be 9, so this became an 81 over 9. And I could tell that I'm not going to get x. Even if you don't work it out to simplify it, you can see it's not going to cancel, you're not going to get x. So that means that f of x and g of x are not inverse functions. So one-to-one functions, a function f of x must be one-to-one in order to have an inverse function, f inverse of x. So remember, one-to-one means it passes a vertical line test, which means the x's don't repeat, and it passes the horizontal line test, which means the y's don't repeat. Now, if it's not a one-to-one function, it can have an inverse relation, but it can't have an inverse function. So in order for the inverse to be a function, the original function has to be one-to-one. Finding inverses of one-to-one functions, and you'll see my note up here at the top, swap x and y. So you're going to swap the x and y values. So if we look at example 1, first we have to determine, is it one-to-one? So you look at the x values, see if any repeat. None of them do. Then you look at the y values. None of them repeat. That means it's a one-to-one function. So to find the inverse, notice the proper notation. You just swap all the x and y's. So you list your ordered pairs. On example 2, if you look at the x's, none of them repeat, so it is a function. But if you look at the y's, you have repeating y values. So that means it's not one-to-one. It's a function, but not one-to-one, which means the inverse is not a function. Okay, moving on. If you saw that, you see the deals at Target. Okay, finding inverses of one-to-one functions. So if you have a graph, what I did on here in class is I took this, the one that's in black, and I just listed some ordered pairs. So I can see 0, 0, 1, 1, 2, 4. I could see those were all points that were on the graph. This is actually a parabola, so it's y equals x squared, only for a restricted domain for x greater than or equal to 0. So to find the inverse, just swap the values. 0, 0, 1, 1, those are the same, and then 4, 2, and plot them. 0, 0, 1, 1, 4, 2. And then when I draw it in, you want it to be symmetrical across the line y equals x, because that's how one way we know they're inverses. And then you can graph the inverse even if you're not quite sure what the function actually was. Then on the next example, it's what's in the black right here. I picked out some points that were on there. Be careful because 0, negative 4 is not a point on the graph. It appears there's a vertical asymptote here at x equals 0. So clearly the point 1, 0, the point 2, 1, and then it looked like 1/2 negative 1. So I used those as my 3 points. Then I swapped x and y. I went ahead and put my dashed line for y equals x because it's easier to graph the inverse when you can kind of compare it and think about it as reflecting across that line y equals x. So then I plotted the points and drew in my curve. And so what I have in red would be the inverse function. And the inverse is a function because the original was one-to-one. It passes the vertical line test and the horizontal line test. On the next example, f of x equals the square root of x. That's the parent graph for absolute value. It's not one-to-one. It's a function. It passes the vertical line test, but it doesn't pass the horizontal line test. You would have y values repeating. Since it's not one-to-one, then there's not an inverse function. So on part B, we are, what I started by renaming g of x as just y, and then I swapped the x and y. So we get x equals 4y minus 7, and then you're going to solve for y. So hopefully that sounds familiar to you. We did that last year. You're going to add 7, divide by 4. You can leave it as y equals x plus 7 over 4. I chose to split it apart and put it in slope-intercept form, but please remember to rename it with the proper notation. So we would call that g inverse of x. Okay, so I am going to continue on with some more examples. So for this one, we have h of x equals x cubed plus 5. So if I call this y equals x cubed plus 5, and then I'm going to swap x and y and solve for y. So I get x minus 5 equals y cubed, and y equals the cube root of x minus 5. So remember to rename it. H inverse of x equals the cube root of x minus 5. I guess what I should have done too, it says to determine or to decide if it's one-to-one. Hopefully you know what the parent graph would look like. I'm going to call that f of x equals x cubed. So that's going to look like this. And if you're going to add 5 to that, that means we're just going to raise it up 5. So clearly that passes the vertical and the horizontal line test. So it is one-to-one. So then that makes sense that we went ahead and found that. Okay, on the next one, this one's going to be a little bit more complicated with the math that you have to do. Now, think about why they said x can't equal 5, because then it's not part of the domain because you'd be dividing by 0. So we're going to start the same way. So I'm going to say y equals negative 3x plus 1 over x minus 5. And I'm going to swap x and y's. Notice there's two places where x's are. So I'm going to have x equals negative 3y plus 1 over y minus 5. So what I want to do next is get rid of the fraction. So I'm going to multiply both sides by y minus 5. So I get this. And you're going to see a process. I'm sure we've done this before. What we're going to do is distribute, because I've got y's on both sides, regroup, and factor. And I don't think it's the first time you've heard me say that. If it is, it will not be the last. So I start by distributing. So there's that step. Now I'm going to regroup, and that just means get the y's on the same side. So I'm going to have xy plus 3y, and I'm going to add the 5x to the other side. I'll put it first, 5x plus 1. Okay, so that is the regroup. And now I need to factor because I need to pull that y out. So I get y times the quantity x plus 3 equals 5x plus 1. And now I'm going to divide by the x plus 3. So I get y equals 5x plus 1 over x plus 3. And now I'm going to rename that in the proper notation. So f inverse of x equals 5x plus 1 over x plus 3. And I need to make the statement that x cannot be equal to negative 3, because if it was, we would have a 0 in the denominator. Okay? All right, so now what do you do when you need to find the inverse of a function with a restricted domain? And you might wonder, well, why would you even need a restricted domain? So let's think about the function f of x equals x squared plus 4, and what if we didn't have a restriction on that? So, think about f of x equals x squared plus 4 with no restriction. Well, you guys know that's just the parent graph of the parabola that's raised up 4. So it's something like this. Okay, clearly this does not pass the horizontal line test. So this is not one-to-one. It's a function, but it's not one-to-one. And since it's not one-to-one, the inverse can't be a function. So if we want the inverse to be a function, we have to restrict the domain. So we have to restrict the domain in a way that it would pass the horizontal line test. So that's kind of what they did on this problem by restricting it just to the x less than or equal to 0. So basically it's saying, okay, we're just going to look at this part of it. So notice if I only looked at that part, then it would be one-to-one if I'm just looking at that restricted part. So that's what we're going to do. So I'm still going to approach the problem the same way. So I'm going to say y equals x squared plus 4. I'm still going to swap x and y. And now I'm going to solve this. So I get x minus 4 equals y squared. And when I solve for y, I'm going to square root both sides. But remember, when we do that, that we're going to end up with y equals plus or minus the square root of x minus 4. So make this a little smaller here. So that's two branches. The square root of x minus 4, if you were just looking at y equals the square root of x minus 4, you'd be looking at a graph that was the square root function moved 4 to the right. So it would be something, like this. And if you were looking at the negative, y equals negative the square root of x minus 4, what's going to happen to that one is it's going to be reflected down like this. So you're going to have something that looks like this. So how do you know which branch that we want? We don't know, so we have to figure out how we can tell that. And it has to do with this right here. For inverse functions, you're swapping x and y. Okay, so think about that. So for my domain, so for f of x, the domain is x is less than or equal to 0. That means that the inverse, the range, is going to be y is less than or equal to 0 because we swap x and y. So the domain of f of x becomes the range of f inverse. Remember, we swapped all the x and y values when we had some things in charts. So if the range has to be less than or equal to 0, then that means we want this part of the graph. So my inverse is going to be the negative portion of that. So I would say f inverse of x equals negative square root of x minus 4. Okay, so that's how you determine which part of the graph you would want, which part you would need. Look at the domain. Remember that the domain of the function becomes the range of the inverse function. Okay, so let's think about this one. Think about what you know this picture looks like. This is a parabola. Move to the right one. But we've had a restriction placed on it, so that we only want the values x greater than or equal to 1. So it's going to be kind of, I guess let's call it a partial parabola, and that's going to make it be a one-to-one function. So the vertex would have been at 0, 0, but it moved to the right one, so that's actually this point right here, 1, 0. From that point, I know if I go over 1, I go up 1 because it's not stretched. I mean, if you did, you could always plug the point in. Plug in a 2 and you'll get 1. If from the vertex, if I go over 2, I would go up 4, so I get this point here. Or I could plug in a 3 and notice what you get. You would get 4. So here's my graph. So this is what I have going on. So if I want to think about the inverse, and I can actually graph this without even doing the function. So if I wanted to know f inverse, I know that I'm going to need the points, instead of 1, 0, I'm going to need the point 0, 1. Instead of the point 2, 1, I'm going to need the point 1, 2. And instead of the point 3, 4, I'm going to need the point 4, 3. So I can plot those, 0, 1, 1, 2, 4, 3. And remember the symmetry to the axes, to the line y equals x. So you can kind of see that. And then I'm going to get something that looks like this. And you can see clearly that that's a one-to-one function. It would pass the vertical line test and the horizontal line test. So let's take a look at what the function would be. So if I change this to y equals x minus 1 quantity squared and swap the x and y, and I have to solve for y. Now don't multiply this out because you're going to end up with a mess. Let's just undo, we're just going to undo the squaring. So we're going to square root both sides. So I'll get just y minus 1. But remember, that's going to be plus or minus when I square root both sides. So that just square rooting cancels out the squared, so that's why I just have a y minus 1. Then I'm going to add 1 to both sides, so I'm going to end up with y equals, I'm going to put the 1 in front, plus or minus the square root of x. But then I have to decide which is it. Is it 1 plus the square root of x, or is it 1 minus the square root of x? Because those are going to be, different graphs. So I can look back and say, since the domain of f of x is x greater than or equal to 1, then the range of f inverse of x is y is greater than or equal to 1. So think about what would give you a range greater than or equal to 1. 1 plus something that's going to be positive, or 1 minus something that's going to be positive. So it's going to have to be the positive version. So f inverse of x is going to be 1 plus the square root of x. Now we need to put a stipulation on this, or a restriction, that this is true for x greater than or equal to 0, because you can't take the square root of a negative. So we would have to have that. So this is our equation for the inverse. All right, so this next problem, f of x equals the square root of x minus 1. And you might say, well, wait a minute, I thought it has a restricted domain. Well, this one automatically, it already has a restricted domain. They didn't have to list it because we're just supposed to know it. We know that x has to be greater than or equal to 1 because you can't take the square root of a negative. And that's a little different from the other ones where we didn't have that automatic restriction that we already knew about. So this one we have to, kind of think through that because we're going to use this later when we're trying to decide which piece we need. So I'm going to do the same thing I did on the last problem and go ahead and make a graph. So if I plug in a 1, 1 is the smallest it can be. So if I plug in a 1, 1 minus 1 is 0, the square root of 0 is 0, so I get the point 1, 0. If I plug, I want to plug in a 2. If I plug in a 2, 2 minus 1 is 1, the square root of 1 is 1, so that's the point 2, 1. I don't want to plug in a 3 because 3 minus 1 is 2 and the square root of 2 is not a nice number. But if I plug in a 5, 5 minus 1 is 4 and the square root of 4 is 2. So I want to plot the point 5, 2. So you want to pick some smart values. So this is what the graph looks like. And that, is confirmed with the idea of a square root function. You know what the square root function looks like. And this has been shifted 1 to the right, so that should make sense. So then for my inverse, I'm going to swap points. So for f inverse of x, we're going to take, instead of 1, 0, we want to plot the point 0, 1. Instead of 2, 1, we want to plot the point 1, 2. And instead of 5, 2, we want to plot the point 2, 5. So we've got 0, 1, 1, 2, and 2, 5. When we draw that in, we can see it looks like this. So we can see that visually. Now, when we do this algebraically, we're going to take, I'm going to call this y, so we're going to have y equals the square root of x minus 1. Swap x and y. Then I'm going to need to square both sides, so I get x squared equals y minus 1. So then y equals x squared plus 1. But this is a parabola. We know what this looks like. It's the whole thing. So we don't want the whole thing because that wouldn't be a one-to-one function. We only want part of it. Now we already know which part we want because we graphed it. So we know we want this portion on the right. But how do you do that using the values? Well, it comes back to this again. So since the actually, to say that this is true. So the domain is x greater than or equal to 1. So that means for my inverse function, the range has to be y is greater than or equal to 1. But that doesn't help much because look up here. Both pieces, both sides, the range is greater than or equal to 1. So that's not going to help me make my decision. So what I'm going to look back here again, though, and I'm going to look at what I have in blue, and I'm going to say, what's the range? So look at the range. The range is y is greater than or equal to 0. Okay, so that's the range of my function. So then the range of the inverse is actually, it's the domain because we're swapping. So the domain of the inverse is x is greater than or equal to 0. So that's what helps me decide on this piece. So this is true that the domain of the function becomes the range of the inverse, but it's also true that the range of the function becomes the domain of the inverse, and that's what I had to think about so that I could know which piece. So when I write my answer on this, I'm going to write f inverse of x equals x squared plus 1, but then I have to restrict the domain, and that's going to be x is greater than or equal to 0. All right, so the last thing I want to talk about, there are some important facts about inverse functions just to kind of summarize those things. The domain and the range swap. So just like the x and y values swap when you're trying to find what it is algebraically, remember that the domain, all the possible x values, and the range, all the possible y values, are actually going to swap. So the domain of a function becomes the range of the inverse and vice versa, with possible restrictions. The second thing, graphs are symmetrical. Graphs of inverses are symmetrical across the line, the identity line, y equals x. So that's always a good reference point to take a look at. And lastly, if you take f inverse of f of x, you get back x. Okay, they undo each other. That's the idea of inverse. And f of f inverse, you get back x. Okay, they undo each other. And that's true for all x in the respective domain. So that takes care of all the notes for this particular section. You should be able to do the problems in the textbook. I know there are additional problems on the handout that you have with the notes. We will probably do those at some point, but you'll have to just wait and check the assignment.